Good morning or afternoon or whatever. This is E637. I'm Charles Bouman, and we're doing image processing today. We're going to pick up on the material in C programming, and actually, we had our previous lecture canceled due to a snow emergency. But it'll probably all be invisible to you in TV land because we're just going to do a recorded makeup lecture immediately following this one. So anybody wants to just stay for an hour after this, we'll do it's like a double header in baseball, okay? We're going to do a double header, and we're going to make up 2 lectures, okay? So we'll be back on track again. And one word of warning to everybody who's taking this course. Do not fall behind on the labs, okay? So there's, I think, lots of resources out there for you to get your labs figured out. You can ask your friends, okay? Because it's fine to ask your friends how to do the labs. You just have to do it yourself, okay? You can find out how to do it from them, but you have to physically type it in, okay? And then you can ask me. I've had people ask me questions. They didn't know the answer to a question, so I actually just emailed them back their verbatim answer that they could cut and paste into the lab. Okay, all I asked is that they read it first and try to understand it. So there's no kind of special secret here. Everybody can get 100 on the labs, but you can't get 100 if you don't do them. And if you don't do them, you get a 0. Okay, I don't know if you know how that works, but if you average a 0 and 100, you get 50, okay? So 1 0 can ruin your entire semester, okay? It can ruin your day. So don't fall behind on the labs, okay? Okay, now, I want to talk a little bit about memory allocation. Well, I want to talk about the relationship between software and computers, because it's really important in signal and image processing, because you can write equations down, and in theory, any equation that's well-defined can be evaluated on a computer, but at least to some degree of accuracy. But the problem is that it may require an enormous amount of computational resources. And there are basically 2 kinds of computational resources, roughly speaking. There's actually, there's computation, there's memory. Those are the first 2. And then there's actually a third, which is actually easily as important as the other 2. And it's communication resources, okay? But because, bus bandwidth and so forth. But let's just focus on computation and memory. It's very often what happens is students will write a program, and the program will take, it'll be running for a few days, and they just won't have any idea when it should terminate. So they don't know. It could be in an infinite loop. It could be just going around in a circle. Or it might be that the thing that they're doing is very computationally intensive, and it's going to take a week. But you need to know. I mean, so you have to have a basic sense of how long a program should take to run. And you can get that within a factor of an order of magnitude or so by just looking at what the operations are that your program is performing. For instance, if you have we're going to talk about FIR filters later. In an FIR filter, we'll calculate the number of multiplies per output point. If you have 1 million pixels in your image and you're filtering it with a window, you've done filtering in the labs, with a window that's, I think in the lab it was 9 by 9, right? So there's a simple case. 9 by 9 is 81 pixels. So every output pixel takes 81 pixels. 81 multiplies, 81 adds. Okay, so roughly speaking, so you take that 81, you multiply it by 1 million pixels. If it's 1,000 by 1,000 image, so it's 81 million multiplies. So how long does it take to do 81 million multiplies? Well, if you have a processor that's running in gigahertz, okay, and it can do roughly an operation per clock cycle. So gigahertz is 1 billion operations per second, and now you have about 100 million operations necessary to actually compute the result. Right, 81 is approximately 100. Okay, so it's 100 million. So that's should take 1/10 of a second. Or maybe, you could be off. It's a 3 gigahertz processor, so it should be 1/30th of a second. But, the thing is often not coded perfectly. Maybe there's a lot of inefficiency in your code, and the processor isn't optimally processing. So you divide by 10, okay? It should take maybe a second. Maybe could take a little more than a second, could take a little less than a second. But if it takes an hour, you know that something's not quite right, okay? So you should have a basic idea of how many operations your program is doing and how long it should take for that number of operations to occur on your computer. And if it takes a lot longer, or even a lot, or way too little, then you know something's wrong. I mean, if you write a program that has, 300 trillion operations and it runs in a fraction of a second, then you know that maybe something didn't work right. Maybe you exited from the program before you should have. Okay, so that's one thing. Now the other thing is memory, and for that I'm going to draw on the pad here. So maybe we can switch over to the pad. So in memory, what happens is that if you know you have an image, and say the image is of width times height, so that's the number of pixels. But you don't know what the width and the height is in advance, right? So you need to allocate memory to store the image in the memory, but you don't want to allocate that memory in advance because then you'd be wasting a lot of memory, or you'd be limiting the size of the image you can use. So it's in programming languages, it's important to be able to do what's called dynamic allocation. So the memory in the computer is like a long list, and what happens is usually there's some part of the memory that's protected. If it's a multi-user system like Unix, then the memory is protected, and it doesn't allow you to write just anywhere in memory. If you try to write out of your particular domain where you're allowed to, of the memory you're allowed to use in your program, then if you try to write out here, you'll get what's called a segmentation fault. So if you get a segmentation fault and the program halts, or what they sometimes, I don't know if does the operating system still say it does a core dump? In Unix it says that, right? So yeah, okay, so it does what's called a core dump. Okay, so you know why it's called a core dump? Well, it used to be, there was a thing called core memory. So they had, before they had solid state memory, they had little wires like this. It's like basically a fabric. And they had little pieces of ferrous material, iron, that were wrapped around here, and they would magnetize them in one direction or the other. And each of these little cores held one bit of information. So this was called a core memory, and a core dump meant it dumped out the contents of the core. So, and in fact, in the computer, when you get when the program halts prematurely due to some sort of error, system level error, one of the options is that it'll write out the memory in your a mapping of all the memory that you had, so that you can go back and see what went wrong when it failed. But one of the failures, and there's more than one, is called a segmentation fault. Segmentation fault happens when you either try to read or write a value outside of your allocated memory. Now, what happens when you need to allocate more memory? You go to the operating system, and there's special subroutines that will allocate the memory from you. So one of them in C is called calloc. Okay, and I even forget what the arguments of calloc are right now, but basically calloc returns a pointer. So this is a pointer, and a pointer is a pointer is a data type that varies depending upon the machine, because pointers are different sizes on different machines, but it might be typically an integer. On a 64-bit machine, it has to be a word. So it has to be, if it's by definition, a 64-bit machine means that it takes 64 bits to address a location in memory. So 2 to the 64 is some very large number. I forget why. But 2 to the 32, I think, is something like 8 gig. Is that right? It's either 4 or 8. I forget. Is it 4? The memory allocation on Unix was 4, but I think it was you could use half of that because they needed 1 bit for something else. Okay, but it's either 4 or 8 gig. And when they had 32-bit machines, and you're probably too young to remember now already. It's really frightening. So when did they switch over from 64 to 32?
3 years ago.
3 years ago? Oh, okay. You're not too young yet. Okay. You will be next year. Okay, so in 3 years. Okay, so what happened was that they could only address up to 4 gig of memory because this address wasn't large enough. So now they went to 64 bits. So the pointer may be actually a 64. Now there might be some complicated encoding process. I don't even know what happens in hardware. It's all invisible. But the pointer stores that address. So calloc, basically, what happens, the operating system frees up a piece of memory, and it may be at a different place in memory space than where the rest of your program is. It's not guaranteed. You don't know. But when you call it, you tell it what kind of data type you want, and you say the number of them. I don't know which one is first. I can't remember. Is it n first or is it the data type? Data type. So this is size of, and you put in here whatever it is. Say int. Now an int is on say a standard machine these days, and it is 8 bytes. Is it 8 bytes? I'm getting confused. Okay.
8 bits, and then you have
8 times 8 is 64. Okay, right. So it's 8. It's an int is 8 bytes, so it's 64 bits. Okay, and a short is 4 bytes. Is that right?
I think you mean bits.
Wait, I'm getting confused. An int is hold on. A unsigned char. Okay, let me do this because we'll need to do it anyway.
Should be 256 for an unsigned car, right?
Unsigned char. That's 1 byte.
Right.
Which is 8 bits.
0 to 255.
Right. So that an unsigned char takes on values between 0 and 255. If it's a signed character, then it uses unsigned. It uses 2's complement arithmetic. So it goes, I think, between 128 and 127. It's either that or 127 or 128. But I think it's minus 128, minus 128, and to 127. Okay. So this would be signed. This would be a character.
Yeah.
And that's also 1 byte. So the difference between an unsigned character and a character is just if you store a number in there, how the CPU handles it. When you add 2 characters together, if they're unsigned, it'll add them together until you get 255, and then it'll wrap around to 0 again because it's modulo 256 arithmetic. But if it's a normal character, it'll treat it as a 2's complement number, so you'll get signed values. You can get the values between minus 128 and 127. And you can actually retype the same data value, and then it'll just reinterpret the same binary values. Okay, we'll get into that later. So then there's a short int. I think a short int is 2 bytes. And then there's an int. Now, this isn't necessarily always the case, but on most architectures, I'm pretty sure that an int is 4 bytes. Okay? Now, on a 64-bit machine, I'm not even sure these days because I don't do a lot of programming. But a long int is probably 8 bytes. Is that correct? It actually depends on the machine and the compiler. It's not standardized. Okay. And then a float is 4 bytes. Now, any of these can be signed or unsigned. If they're unsigned, then they're 2 complement. If they're signed, then if they're signed, they're 2 complement. If they're unsigned, they go from 0 to 2 to the n minus 1. And then there's a float, and then there's a double. A double is 8 bytes, I think. And but the actual word size on these machines is 64 bits. So I don't know if they have special types to support that. They probably do, but I haven't been following it that closely lately. Anyway, these are the basic types that get used most often. And okay, so now, but no matter what type you have here, the pointer is always going to be really the same from the point of view of the physical representation on the computer. Because any pointer is just something. So let's say you have a size of an int, then it tells you each element has got to be 4 bytes long, because an int is 4 bytes. So, and you're going to get n of them. So it's going to get 4n bytes of memory for you. So it's going to get 4n bytes of memory, and then the pointer is a thing that points to the first entry in the array, and it's going to return the pointer to you that points to that first element. Okay. Now, what you can do is, let's say you did the following. Okay. If you do this, you say, okay, I'm going to let's say I do the following. I say, okay, I'm going to allocate a pointer. I'm going to say the pointer. Okay, let me do this again. Let me start again. Okay, I'm going to have a pointer. The type here is going to be, say, a float. Should I make a float? I'll make it an int. Okay, star pointer. So that says that this points to an int. Okay, and I'll call that pointer 1. Okay, and then I'll have a character. And I'll make this pointer 2, right? And yeah, okay, so that's good. So now what I do is this: I say, okay, let's say I say, okay, now in addition I say, int is let me do, okay, when I'm going to do that, I'll say, okay, I'm going to get an array, and I'm going to put it into pointer 2. And I'll put this unsigned, so this will be a character, star, alloc, and then a size of character. That basically just means 1 byte. I could have actually just put a 1 there, but this is the convention for how you do it. And then I'll put here, I don't know, 100. So that's going to get me an array of 100 bytes, okay? And now what I can do is I can say, pointer of 0 equals 0, and I can say pointer of 1 equals 1, say. So now what I've done is, in memory, I allocated an array of 100 bytes, and the first element here I put a 0. This is pointer, and the second byte here points to pointer plus 1. So when I add 1, hold on for a second. This is called pointer 2. That's important. I got to put a 2 here. Oh shoot. I'm sorry, this is sloppy. Pointer 2 plus 1. Okay, when I add, the key here is that pointer 2 is a pointer to a character. Now, every pointer just is a memory address. But the compiler knows that this is supposed to be pointing to a character. So if I add 1 to the pointer, so I could have also done this by just saying, I could say pointer 2 star equals 0, and I could say star pointer 2 plus 1 equals 0. And it'll put, or 1, it'll put a 0 here and it'll put a 1 there. Because when I add 1 to pointer 2, it knows pointer 2 is a character pointer, so it knows if I add 1 to it, I have to increment 1 byte, because a character points to a character pointer points to the characters are only 1 byte long. So if I move by 1 character, I've moved by 1 byte. Okay. Now, in C will allow you to do some truly perverse things, because what you can do now is this: you can say that's the beauty of C is like it's like a chainsaw. Okay, you can do a lot of good and you can do a lot of damage. Okay, okay. So what you can do is this: you can say pointer 1 equals pointer 2. And you can say, well, hold on, I can't do that because this is a pointer to a character and this is a pointer to an int, okay? And you could say, oh, okay, well, that's okay. It's just really pointing to something in the machine, so I'll just retype it. I'll put int and I'll star, all right? And that's fine. And then what'll happen is that, and then I could say things like, I don't know, I could check the value of pointer 1 star. And pointer 1 star will be, it'll be the integer that's stored here. Now, I don't even know what's in these second 2 bytes. And in fact, it might have been some leftover junk from the last program that ran, okay? Because alloc doesn't guarantee that memory is zeroed out. There's another version of this called malloc, which zeroes out the memory when you get it. But that's a little extra computation. So they give you the option. They go, well, do you want the chainsaw with the chain guard on, or would you like the chainsaw with the chain guard off, okay? Okay, that's fine. I'll take the chain guard off because I really want to go to it. Okay, so what'll happen is you'll get like random data in here, but there'll be some integer. And you'll read that value, and you'll get some crazy value out of there, okay? You might actually be interpreting the value of some program instruction to the machine that was last stored there, but you'll read it, and you can display it as an image if you want. It'll look like a crazy image, okay? But you can do it, you know? That's the beauty of C. It'll just let you do anything, okay? Now, actually, there's some security issues here, too, right? Because if this is the leftover memory from somebody else's program who was like, you know, I don't know, like the CIA or something, then you got some problems. And actually, one of the most renowned bugs in Unix, the source of the granddaddy of all bugs, okay, is what they call the buffer overflow bug, right? You basically just overflow the buffers in like a standard program like LS or something like that. And then it allows you to violate memory partitions, and then you know once you get root password, you just go to town. I remember when I was a graduate student, one of the first guys. This was before the internet had very good protections. I mean, I don't know if they're very good now either. But some poor slob, he was a graduate student, and he wrote a worm, okay? Because worms were like a new concept that did this, and it completely brought the entire internet down. And the poor guy, the FBI arrested him. I don't think he had any idea what he was doing at the time. Okay, but yeah. So anyway, all right. Okay, so there's interesting security issues. So now, okay, but now this is the interesting thing. Now what you could do is this. You could say, well, I could also take pointer 1, and I could set it equal to, I could retype this thing. I could take pointer 2, okay, and I can add 1 to it. Right? So I can take pointer 2. If I take pointer 2, I'm going to increment it by 1 character. And then if I take that pointer, it's a valid pointer, and I store it in the pointer for pointer 1. But now this thing thinks it's looking at integers. And what I can do is I can then try to read pointer 1 by actually reading the value at that position. The star here means take the value at that position, right? This is like, emergency flares go off. Because now this is, now you're going to pay the price for not having put the chain guard on, okay? Because here, this is violation. Because you're asking the machine to physically do something it can't do. the computer does not physically have the capability to read that value because it's in the wrong location. See, what happens is this. This first entry here is 0, right? Its position is 0. That's like the first location in memory. There's got to be a first location in memory, right? So, and then the second location in memory is 1, and the third is 2, and the fourth is 3, right? And then you have 4, right? Well, if you want to read an integer, which is 4 bytes, it's got to fit at a boundary that's divisible by 4. In other words, it doesn't let you just put the integer anywhere. It has to be aligned with the bus. I mean, if you think of it physically, the bus is like, back when they had like 32 bits. 32 bits is 4 bytes, right? No, I'm getting right. Yeah, 1632. Back when they had 32 bits, you literally had a bus, right? That had 4 bytes on it. Now the bus has 8 bytes on it. And the bus would read into memory. It's lined up with the memory. So it can write here and it can write here, okay? But it cannot write in between. This is like asking you to drive down the highway along the median strip, okay? So you know you're asking it to read here. You're not aligned with the bus. This causes a bus error. So if you get a bus error, that's what you've done. Now you'd say, well, why would I do any of these crazy things, okay? Well, you will do them, okay? Especially if you write lousy programs. Because when you're not paying attention, all kinds of nasty things will happen. First of all, this is why retyping of variables is so important. Because if you know you're retyping an int to a character to an int, then you'll know, oh gosh, that's a really bad thing to do. I really shouldn't do that unless I'm absolutely... There are times when this can actually be extraordinarily useful, okay? For instance, if you want to actually... Let's say, this is an interesting thing. You know, there's 2 kinds of machines. There's called big endian and little endian machines. So you don't know whether the first byte of a 2-byte word is the most significant byte or the least significant byte. So you can use this to figure that out while you're running the program. So your program can write an int, say write the int 1, and then you don't know whether the first byte contains the 1 or the second byte contains the 1. So then you can read this character and read that character and figure out which one contains 1, and you can discover whether you have a big endian or a little endian machine, and then you can use that to modify your program to use the architecture appropriately, okay? But, so there's valuable things you could do, but you don't want it, but if you're doing this, you know, it's like you've poured 50 gallons of gasoline on a fire, right? You don't want to do that. I guess it could be a powerful and useful thing to do at certain times, okay? If you want to start you need to burn down a big pile of wood efficiently, right? But you don't want to do it accidentally, okay? So if you type all your now if you leave out this retyping, the compiler will give you a warning because it'll say you've assigned 2 variables, you've assigned 1 variable, you have a type mismatch. It'll tell you there's a type mismatch. So if you write this into your both will compile. So I can leave this out. The code will compile. It will compile. It will just give you a warning. And people say, who cares about the warnings, okay? Well, the thing is, if you put this thing in here, it means you were fully aware that you were doing this very dangerous thing. You were pouring gasoline on the fire, okay? So don't worry. The fire engines are parked right down the street, and I've got a fireproof vault around the thing. And, you know, we've all taken appropriate precautions. We know exactly what we're doing. As opposed to, hey, Joe, could you just pour that gallon of gasoline over there, right, and see what happens? Okay? So by retyping, you know exactly what's happening. If you get a bus error, a segmentation fault, it means you've handled memory incorrectly, okay? Now, let me explain how this happens. When you get allocated memory, you'll have this pointer, which is, say, equal to calloc size of int, okay, and then say n, okay. Now what will happen is there's a couple ways that you can get a segmentation fault. One is that when you go to read this thing, you took this and you took n plus 1. Because n plus 1 is not a valid member of this array. You run off the end of the array. So actually, this even n is off the end of the array. So this is actually 2 entries off the end of the array. This is p of n plus 1. So this may generate a segmentation fault. It's not guaranteed to generate a segmentation fault because you might get lucky, okay, except for it's really unlucky, and you might find that you just happen to hit a piece of memory that you were allowed to, okay? It'd be like you wanted to demolish a building, okay? So there was some building, and they were going to pay you $100,000 to demolish it, right? Then you have like a thing you drop on a bomb to demolish it, right? And you say, well, I've decided that I feel lucky today, so I'm going to fly around in the airplane with my eyes closed and drop the bomb in a random position, okay? And it's going to hit in a farm field here, and nobody noticed that it went off. Well, that's sort of bad because now you don't know that you've done something really stupid, okay? That could be dangerous, okay? So it's bad that the thing doesn't, it's bad that it doesn't get a segmentation fault. It's actually better to produce a segmentation fault because now you know you've done something that's very dangerous, okay, and that you don't want to do. Yeah. Okay. So this actually raises an issue. When you have a program, if you have a program and you have lines of code, and what'll happen is sometimes what'll happen is you'll have like a code, right, and you'll have x equals x plus 1, right? And then you'll have y equals y plus 1, right? And you'll find that if I swap the order of these two lines, the program runs fine. And if I don't swap them, then I get a segmentation fault. So what do you do? Is it better to swap them and have the segmentation fault, or is it better to leave them unswapped? Or is it better to swap them and stop the segmentation fault, or is it better to leave them unswapped and have them run correctly or something? Yeah, you want to, so this is the part that's very counterintuitive, okay? When you're writing code, you want to go looking for trouble, okay? You want to, if you see anything goes wrong, you don't just try to keep going forward with the wrong answer. You don't try to make some kind of random change and say, I don't know why it's working now, but it wasn't working before. No, you want to reproduce the results that caused it to fail, particularly if it's a segmentation fault, because you can have a bug in a program, you can be indexing outside of the array, but not generating a segmentation fault just because you're unlucky. The lucky thing is to have the actual segmentation fault occur, because then you can actually figure out what went wrong. Okay? So, yeah. Okay. So now let's see. I'm just trying to think. Okay, so now what happens is things get a little more complicated. So the bus error occurs. By the way, what will end up happening is that once you start indexing outside of arrays, then you start just randomly changing pieces of information. Often these might be pointers out here. So when you go to use those pointers, you'll now point to things that are crazy. You might get a segmentation fault because your pointer now points outside of your memory, or you might get a bus error because the pointer now points to an invalid location inside of your memory. All right. So the memory allocation bugs are the most difficult bugs to debug. The most difficult bugs to fix. You can spend lots and lots of time. So when you design your memory allocation for a program, you have to be very careful to use a very clean architecture. There are also tools that help now. They do bounds checking. And programming languages like Java, I think, are much better because they're designed to do a lot, to basically not allow you to take the chain guard off, okay? So, but the downside for that is they tend to be less efficient. Java has to be more careful because it needs to be a more secure environment. And a lot of these things can lead to security problems. Okay, so, yeah, there was one other point I wanted to make. Okay, so, it'll come to me. Yeah, I know. Memory leaks, okay? So we talk about segmentation faults. So a segmentation fault occurs when you try to index outside of the available memory, and that's often because your arrays are writing outside of their bounds, okay? Because there's no bound checking in regular old C, okay? When segmentation fault is actually the desirable outcome because you know a failure occurred. The undesirable case is that you actually just wrote outside those bounds, in which case you could have modified pointer values, and those things can cause bus errors. One thing that can happen is that when you have these bus errors, they can occur. So you may get a bus error on line 1000 of your program. And you search all around because the line of the program that's giving you the bus error is perfectly valid. The reason it's giving you the bus error, or it may give you a segmentation fault, is because the pointer that you're using, so you have an array, this pointer has been corrupted. And the pointer may have corrupted 100 lines ago. So the reason that the memory faults are so hard to find is that the error doesn't occur where the bug is. It's as if, like, you made it, like you did something wrong here, but the failure occurs 100 miles from here. Okay, so it becomes very hard. So bus errors occur when you index it to wrong location. Both of these can occur because of the fact that pointers get corrupted. Okay. The other thing is memory leak. And a memory leak, the problem is that that what happens if I allocate a pointer size of char n, okay, and then I say, okay, I'm going to set the pointer equal to 0. Okay, what happened now is I allocated n bytes of memory, and I put a pointer to here. So this is the address. This is as if I went and took this data, and I put it in a locker in the airport, and I have the key. This is like a classic plot from one of these spy movies, okay? And then the spy is lost, okay? So now the key's gone, okay? Once I write over the pointer, I no longer know where that memory is. This memory is lost. It's as if you've eliminated that memory from the computer. It's no longer available for use. This is called a memory leak because you are effectively leaking memory out of your program. And I won't name names, but there've been some like famous examples of commercial software products that are widely used that have memory leaks in them. Okay, so what'll happen is that if you run the program, it's like my program, you run. Okay, it's some program. It comes up, and you're using it, and you're doing your stuff. Okay, and then what happens is that if you watch the memory allocation, using the operating system tools, you'll notice that the program keeps using more and more and more memory, okay? Until finally, it's used up all the memory in your computer, and then either your computer crashes or the program crashes, okay? And then you reboot and you start again, okay? That's called a memory leak. So the only way to release that memory back to the operating system is to basically quit your program. Terminate your program. Mm-hmm. So what you should never do this. When you're finished with the memory, you free it. And this basically passes the information back to the operating system and allows the operating system to pass that memory on to other users or back to your own program. Actually, I think in a lot of operating systems, it never really frees it back, the memory back to the operating system completely, but at least it makes it available to you again. For if you reallocate memory. You can also have problems like memory fragmentation, that if the pieces of memory get to be too small, when you allocate a big chunk of memory, it has to be contiguous. But memory leaks are the worst, okay? Okay.
Can I interrupt real quick?
Yeah.
In those examples of the operating systems that don't return it to the user space, but keep it for that one particular process, would the heap just continue to grow if you continued to allocate?
I'm sorry, say that again?
Would the heap continue to grow if you continued to allocate? Or would you... Would that be... So if you freed a variable...
Okay.
Would the heap... And you said that doesn't go back to the user space.
Yeah, okay, right. So the heap... Okay, would the heap continue... Okay, so if you free memory back up and you... First of all, I don't think C makes any guarantees. It could be the case you could have a valid implementation of a C compiler that does nothing when you call free. Okay? Because, it still compiles and the program still runs, okay? So there's a question as to what they actually do when... And I think that can be... My understanding, and I'm not an expert on this, frankly, is that this can be OS specific and it can be it might be, OS specific, okay? But usually what ends up happening is, in my experience, and these things may have changed because I haven't looked at it recently, is that, it releases it from the heap, and then what happens is that further allocations inside your program can use that memory.
Okay.
But it doesn't necessarily release it back to the operating system.
Right.
Usually it doesn't.
Okay.
It probably gets too hard to do it, okay, because the memory has to probably be contiguous. Yeah.
Okay.
But in theory, it could release it back to the operating system. I mean, if you had a very sophisticated operating system.
Right.
So, okay. Now, the other thing is multidimensional arrays. So C has no real honest-to-goodness support for multidimensional arrays. So what happens is that we have a thing called multi-alloc, which a student here wrote. Well, actually, it was a modification of a piece of open-source code. But the, I use this, and I give it to you to use, but the concept is not... novel. I mean, it's just an implementation of a basic idea, which is that you have a pointer. So, say to ints, but it's a doubly indirect pointer. So this pointer here points to an array. Okay? And this array is an array of pointers. So each of these pointers points to the first element of a row. Now you can continue this and you can make this a three-dimensional array or a four-dimensional array, right? And the advantage of this is that that you can pass this one pointer and it gives all the information to access all this data, right? The disadvantage is that it's a little bit complex and you're wasting this extra memory here of this array of pointers. Now, this array of pointers is usually not a very it's usually not a lot of wasted memory, as long as if this is an image, which is say 1,000 by 1,000. Then that's not so bad because it's only a 0.1% of wasted memory, assuming that this element. Well, actually, this is a pointer, so it's a lot more data than one element of an image, which might be an unsigned character. But where it would be bad is if this last dimension was small. So what you wouldn't want to do is do this. You wouldn't want to do a multi-alloc where you had a image and you say had the first index was the I, the second index was the J, and the third index was the color. Because this is only 3 dimensions, right? So you would have a 50%, well actually you'd have about 100% waste of memory. So you never, this thing here is called the fast variable. And this is the slow variable. Because this is actually a linear array of memory. So in other words, this element here is right adjacent in memory to that element there. So when you index through this array in a linear order, the color would be the fastest changing variable. The last variable is the fast variable, and the first variable is the slow variable. So you never want this last variable to be very low dimension, because then this would be very inefficient. Good. Yeah, and I think that's pretty much it. So, and then there's a multi-free. And multi-free is a fairly, actually these pieces of code, if you're like an avid C programmer, you might want to look at them. They're kind of clever pieces of code because the way they're written sort of recursively. But basically it goes in and frees this array and frees all the nested arrays. Okay, any questions about this? All right. So how many people... So I guess at this point, people are implementing their C programs, and they've had some success in that. Yeah. Okay, so now we're getting to the discrete Fourier transform, discrete time Fourier transform. So let me start off with the discrete time Fourier transform. DFT. Okay, so far we've talked only about continuous transforms of time. So we talked about the continuous time Fourier transform, and we talked about the continuous space Fourier transform. Now, this is the discrete time Fourier transform. This is sort of the analogous transform for discrete time signals that go from infinity to minus infinity to infinity. So they extend over all time. And this is the transform, and this is its inverse. Now, one of the very important features or attributes of a DTFT. Oh, by the way, since I said it, a DFT or a discrete time Fourier transform is not a discrete time. A DFT, a discrete Fourier transform. So the DTFT is not the discrete DFT. The DFT, which is actually equal to the FFT. The only thing that's different between the DFT and the FFT is this is just a fast algorithm for implementing that. Okay, they're the same transform. Okay. That this is not this because this is over a finite length sequence. So it's very different because the DTFT turns convolution into multiplication, which is the same thing with the continuous time Fourier transform. But the DFT does not convert convolution to multiplication. It converts periodic convolution into multiplication. But convolution in a linear time invariant system is not periodic convolution. So the DFT is really misnamed. This should have been probably called, if people were to go back and rename it, it should have probably been called the discrete time Fourier series. Discrete time Fourier series. Okay? Because as with the continuous time Fourier series, it works for signals which are periodic in discrete time. Okay? So I know there's often a lot of confusion about that. We'll come back to that later. But the DTFT is the Fourier transform of an infinite discrete time signal. And the corresponding Fourier transform is periodic with period 2 pi. So you only really need to know its values between minus pi and pi, and then you know it everywhere else. So this is the inverse Fourier transform. Okay, we're running out of time. I'll pick up on this next time. We'll quickly go through the DTFT and the discrete space Fourier transform, and then we'll get into some sampling. Great.